Hi everyone, welcome to this video series on word embeddings used in natural language processing. Previously, we talked about the vectorization methods used in text processing. In this video, we shall be focusing on popular word embedding algorithms called Word2Vec. Along with the technical aspects of the model, we shall also be discussing the intuitions and example use cases of the word embedding called Word2Vec. We shall talk about the need for optimization as well when we talk about Word2Vec model. Finally, we will look into some of the shortcomings of Word2Vec model. In terms of additional use cases, we will also talk about how we can extend the concept of Word2Vec to something like document to vec or sentence to vec. Let's get started. So some of the prerequisites, a fair amount of Python and data science exposure, machine learning understanding, deep learning architectures like multi-layer perceptron and typical neural nets, and also decent exposure to natural language processing and some of the packages like GenSim, Spacey, and NLTK. So the topics to cover, I've broken into few blocks here. In this particular video, I'll be talking about the idea of embedding, embeddings and the background, and some of the intuitions or intuitive understanding of the Word2Vec. And then in the subsequent video, we'll talk about the training process for Word2Vec, and I'll do a demo of how embedding layers are set up in TensorFlow and Keras and so on and so forth. So these are the various subtopics that we will be covering as part of this particular video series. So the idea of embedding in natural language processing, let's take some examples here. The first we'll look at the evolution of embedding. It started way back in 1970s with the introduction of one-hot encoding. This is still used in many of the natural language processing applications. TF-IDF, we talked about this in our vectorization series. Latent semantic analysis, which is also based on TF-IDF and count vectorizer. That was introduced in 1985. The one that we will talk about in this video is going to be Word2Vec, and this was introduced in 2013. And subsequently, in 14, there was some improvisation to Word2Vec, and that came in the form of Glove and FastX. And after that, the major introduction was Elmo, which is the first pure language model type, or the embeddings for language model based on bidirectional LSTM. And in 2018, we have BERT and transformers based embedding. And nowadays, we talk about GPT, GPT-2, 3, 3.5, 4, 4.0, and so on and so forth. So that's how the embeddings journey looks like in the last 30 to 40 years. In this video, we'll talk about the Word2Vec. So what are embeddings? Embeddings are vector representations in continuous vector space. Let's take an example here. Let's say you have sentence 1 and sentence 2, and this is the sentence. Natural language processing is fascinating. Machine learning algorithms are powerful. How can we represent the entire sentence in terms of a vector? So for example, this could be the vector representation for sentence 1, and this can be for sentence 2. And how do we achieve it? That's what we will be discussing in this video and also subsequent videos. Some more illustrations. Essentially, idea of word embedding is to capture the meaning or relationship between the word and the surrounding words. For example, the cat sat on the windowsill and was looking outside. So what we do is each word is taken out as a token or a unit, and we represent every word in terms of a vector representation, continuous continuous values, and these vectors represent the word. The essential idea is the just a second. Yeah, the essential idea. The key idea is that the vectors or the word, which should be semantically similar, they should be in the vector space. They should be aligned. For example, if you think the word sat and the should be together, or they are used together, then the vector representation should actually reflect that. That's the basic idea of word embedding. Let's look at some more examples here. Let's say if we are using the word dog, then these similar words can be this cat, dog, rabbit, puppy, poodle, and all of these were Doberman and pig. They should be more or less like a family, and the vector representation for these words should be very similar to the vector representation of the word dog. And likewise, let's say November, with the vector representation for November and the other month, they should also be in closer proximity. So that's the basic idea of word embedding. Why are word embeddings important in AI? Because of the need for semantic understanding. The computers don't understand anything other than numbers or zeros and one. So, in order for the computers to understand the word and the lexical part of the text, there must be some way to convert the text into number, and thereby we achieve semantic relationship. For example, let's say we have vector representation for king, we have vector representation for man, and a vector representation for woman. If the analogy is if a king is to a man, then what is to a woman? Given all these vector representations, then the answer that we expect is something like queen. That is the meaning of semantic analysis. Let's look at some more examples here. One of the examples where the embeddings play a big role is dimensionality reduction. For example, if we have 1,000 movies or 10,000 movies, and they can be represented using one hot encoding, and the dimension of that vector would be, let's say, 10,000 movies. So this is going to be 10,000 dimension vector. Now that's pretty hard to process, 10,000 vectors. So we would like to reduce um, the dimensionality of the movie representation or representing the movie description by using, let's say, 50 dimensional space. Let's look at another example, handling categorical data. For example, product ID and user ID. These are ideal cases where you can embed those IDs for meaningful analysis. Transfer learning is another example of using the pre-trained embedding. For example, for your NLP task like text classification or clustering or other NLP application, we use pre-trained embeddings like Word2Vec, which is what is the subject in this video, and also the embeddings like BERT or Transformer and many others. Those are essentially the use cases of embedding in terms of transfer learning. So summarizing, the word embeddings represent the words or character or sentences or PDF or group of words using continuous values as vector. And the way they are prepared, they enable us to capture semantic relationship between the words. Techniques like Word2Vec and Globe and FastText, these were very popular when they were introduced in 2014, and they allowed, quite a bit of, success in terms of NLP application. So these are also examples of transfer learning. So let's look at the background behind embeddings and how these embeddings typically look like if you just visualize the multi-dimensional vector representation for words or document or PDF or tokens, and then you convert it to a two-dimensional representation, then ideally it should reflect the semantic relations, like words being used together should have similar vectors. Now, a couple of papers for reference that I would like to highlight here. The one that we will talk about is Word2Vec. Then extension of Word2Vec is document to vector. Some more changes or improvisation to Word2Vec is in the form of fast text. So essentially, we'll be focusing on this first, um, paper here, which is about Word2Vec. So the acronyms, Word2Vec is for transforming the word in terms of a vector representation. And similarly, if you convert a document, or could be sentences, could be group of sentences, could be paragraph. And when we do so, that is called document to vec. Sentence to vec and document to vec are sort of related. The technical aspects I'll be showing you after we go through the understanding of Word2Vec and implementation of Word2Vec. So I've divided into two parts. The first one is Word2Vec, and then in the later part of our video series, we'll be talking about document to vec and sentence to vec. Now, a little bit about the bag of word representation as a recap. We have seen this in our vectorization series. Typically, the words are represented using sparse representation, something like this. Most of the values will be zero, and some places the value will be non-zero. The non-zero means the number of times that word is appearing in the sentence. So word embedding can be built for words, can be for characters, for sentences, for paragraph, or even a number can also be represented using a vector representation of random numbers. Discrete variables are also ideal candidates or suitable candidates which can be represented by using random numbers. So word embedding is a term used for representing words using numeric vector. This numeric vector, these are real valued vectors. And essentially the idea is the words which occur together naturally in the comprehension, they should have similar vectors. And word embeddings are also described in terms of distributed representation of text in n-dimensional space. What does it mean? It means if we consider the vector representation of, let's say, 50 values, then the embeddings are distributed over those 50 dimensions. So what are the different types of word embedding? Some of these we have seen in our vectorization series. The first type is called frequency-based, like count vectorizer, TF-IDF, and hashing vectorizer. And similar to this would be your co-occurrence vector as well. Most of these we have covered in our vectorization series. Then the second type of embedding or generating the embedding is through neural nets, as called prediction-based. And the models which are popular are called continuous bag of word and skipgram. We'll be focusing on this second type of word embedding generation, which is through neural net. So let's look at how we can represent the text as numbers. So one of the method is one-hot encoding. For example, if you have this sentence here, the cat sat on the mat. Essentially, first we need to build the vocabulary, which is a unique set of words from your input data. And for example, here, these are the vocabulary words. Now to represent every word, we are going to create a zero vector of the length of the vocabulary, and then the place where you have the word in that index position, we will put 1 here. This is typically the method we have used so far. It's a very simple method. It's called one-hot encoding method. And if you have a sentence, for example, let's say here we create a one-hot encoding vector for cat. Each one of the words we will prepare one hot encoding, and then for the sentence we are going to just sum or aggregate all of the one hot encoding vectors. So finally the sentence would be the encoding of the sentence, which is concatenation of each of the one hot vector for the word. So some examples here, let's say, you have, V number of, tokens or the word, and each word can be represented using one hot encoding where every word has a corresponding one in the vector representation. Similarly, Paris has a one here, Italy has one here, France has corresponding one. This is one hot encoding here. Another example, let's say here the man, woman, king, queen, and apple, and they can be represented using the one hot encoding. And if you notice here, only one place will be having the index of one. Now, there are problems with this method. I've highlighted those two problems here. So what are the problem? Inner product of two vectors. So if you take any two vectors and you do a dot product, you're going to get 0. The distance between any two vectors is also equal. And for example, apple and orange or orange and man. So that's not desirable in our machine learning. So next approach is you can encode each word with some unique number, arbitrary number. Let's say cat has been assigned to 1, arbitrarily mat has been assigned to 2, and so on and so forth. That can be one strategy. And then the sentence can look like this kind of, vector representation. This approach also works in some of the cases. At least in this case, we do not have sparse representation. We have a dense one where every element has a value. But there are downsides here. Since the integer encoding is arbitrary, it does not capture any relationship between the words. Integer encoding can be challenging to interpret in terms of semantics or in terms of interpreting the model behavior. So the next representation type is slightly advanced and more rich, is called featurized representation. Let's take a look at it here. Let's say you have these words and we are representing these words in terms of some numbers here, and these numbers are against some abstract dimension. Let's say gender. The word man would be high on gender. Similarly, woman would be high on gender, king would be high on gender, queen will be high on gender or dimension, apple will be very low and nothing to do with gender. Similarly, food and all that. So for food, you have man, a woman, king, and queen. They will be low in terms of the value, but apple and orange will be high. So this can be useful. The useful in the sense then you have every word having a distributed value across the dimension. Let's say you have 300 dimension. And also now the vectors are different and you can subtract the two vectors, you will get a different value. But again, the issue is practicality, very hard to generate such featurized representation across the dimensions. So essentially the word embedding should be or is a dense representation. For example, comparing here, let's say the word is Obama. And if you use one hot encoding or bag of words representation, TF-IDF, or count vectorizer, you will get this kind of representation with most of the values 0, and some of the values in the vector would be some non-zero. And for example, this is one hot representation for Obama. But in case of word embedding, same Obama, word or token will be represented using continuous values, and all elements or all positions will have some real value here. Now, the advantage here is the number of dimensions of the vector will be much lesser than the dimension of the vector that we are talking about here in case of one hot vector. So the word embedding gives you compression. It also gives you very disc from discrete to continuous representation, which is very good and useful in machine learning, sparse to a dense representation. So summarizing the need for word embedding with the one hot encoding method, the word cat is similar to tiger because the vector representation is just sparse representation with just one place will have a non-zero index. One hot vector dimensionality is same as the number of words. So if your corpus has 500,000 words, the dimensionality of the vector would be 500,000. As you increase the vocabulary, your which feature size is also going to increase, and that results in computational issues as well. So many machine learning models don't work so well with such high dimensionality. Neural nets, but in particular, they really struggle with sparse input. And memory issue is another large constraint that we have when we talk about simple one hot encoding or count vectors or hashing vectors, or we are talking about, let's say, TF-IDF. Some examples where we use embeddings, let's say sentiment analysis, and you're analyzing the movie reviews. So here, each of the word used in the review will be represented using suitable embedding, and that results in better classification or sentiment analysis. Same for classifying news articles. And in fact, for machine translation, the embeddings work really well because of the semantic benefit that you get because of the embedding. Checking plagiarism is another good application where we convert the input data or text or PDF or article into embeddings, and then when you compare those embeddings, it gives much better result than sparse representation. Even for question answering system, using embedding method is more useful. Topic modeling to find out the abstract topics in your data, like let's say PDF. Again, using embeddings gives a better result. Let's look at some more intuitive understanding of embedding, how we uh, get those embeddings through the model. Essentially, for the embeddings, we are talking about surrounding words. So, given a sentence, given a paragraph, we are talking about some kind of surrounding. That surrounding is called context. And this context is defined by number of words preceding the target word and number of words after the target word. And this n is typically tunable or configurable. Larger the size of n gives you much better embedding representation. In the original paper for Word2Vec, the n has been used as 4 or 5 words to the left, 5 words to the right. So the specification of word embedding, the generally 8-dimension embeddings are produced, 32 dimensions are also used, 50 dimension or 600 dimension. Now all of these dimensions are something that we need to experiment with our data. and results, and then decide how many dimensions we want for our embedding representation. If you notice the ChatGPT and the modern LLMs, they are typically around 4,000 dimensions or 8,192. But the vector or embedding that we are talking about, we will focus on 100 dimension and 300 dimension, for example. So how do you build word embeddings? Essentially, you can train your own model to generate word embedding, but requires large amount of unannotated data. It takes hours and hours of training to generate word embedding. The other option is to use pre-trained model, for example, Glow, FastText, Elmo. I have just listed the basic ones. Nowadays, most of the language models like Llama or Bloom or GPTs, they have their own embedding, pre-trained embedding. That's what we use. And this is also called transfer learning. There are extensions to the fundamental Word2Vec, which are called document2Vec or code2Vec or sentence2Vec or paragraph2Vec or could be PDF2Vec. These are extensions that can be built using the fundamental algorithm called Word2Vec. So essentially, Word2Vec, when we talk about Word2Vec, is nothing but group of related models or their extensions here. The neural net that we use to generate Word2Vec is fairly straightforward, very simple neural net, input layer, hidden layer, and output layer. Input layer takes the large corpus of text and it produces a vector space, which is called embedding. Generally, the embeddings are going to be, let's say, 100 dimension, 300 dimension, or even more. And the idea is the words that are commonly used together should be also sharing the similar or close proximity in the space, multi-dimensional space. For example, let's say the word king, man, and a woman, and these are my embeddings. I have used different colors here. Typically means value, let's say 0.7, 0.9, 0.1, and 0.11, and so on and so forth. And this is how the embeddings will look like. So typical embeddings are, let's say this is from Glove, and the embedding is for the word king, and this is 50 dimensions. So there are 50 values here. So similar words should have similar looking vector. For example, woman and a girl, if you look at that woman and a girl here, the vector representation would be more or less similar. And why similar? Because these two words are used together most of the time. Similarly, man and a boy would be also sharing the representation. But if you look at the word water, this can look very different compared to the other, but still there are some commonalities here. So one or two dimensions may be common here. How we generate Word2Vec, the neural net architecture can be these two. On the left hand side, this is called continuous bag-on word, and the right hand side is skiff-gram. Let's take a look at it. What is the difference between the two? So the left side architecture that we have is used to anticipate or predict a given word. So we are predicting a word here by using the surrounding word. That means, let's say we have a surrounding word, W1, W2, and then two surrounding words after the main word here, and we are predicting this word here. So when we are predicting the center word using the surrounding words, the architecture that we use is called continuous bag of word. Just the opposite here, using the center word, we can also predict the surrounding word or the context. So, for example, here I'm going to use W1, W2, and W3, W4 as the prediction by using the input as the center word. So this is the center word. With that, we are predicting the surrounding. Both of the architectures are equally good and they produce comparable results. Let's take an example here. The sentence is quick brown fox jumps over the lazy dog. So here is the surrounding word, left context, and this is the right context, and this is the target word. So the example data that we prepare to train the model, we will be using the left two, generative and the model, and then the and future as the input to the neural net, and we are predicting the center word or the target, which is R here. And just the opposite in the skipgram, we are using input, which is R, and then using that, we are predicting the surrounding word. Both of the architectures are quite good in terms of performance and functionality. The training process would be the next topic that I will cover in a separate video. Thank you all. We'll see you in the next video.